All right, part 3 of our lab is looking at how planetary atmospheres and the molecules in them move. And really, a measure of molecular motion, that's called temperature. It's the average kinetic motion of the molecules in a material. So things like the sun and the planet's interior cause the temperature, the quote-unquote temperature, to change. And what is temperature? Well, it's really just a measure of molecular motion. What I have in front of you is a beaker full of cold water. And I just got this water out of the refrigerator here, and I put the thermometer in for us to measure. And it looks like the temperature here is about 7 degrees C, or about 40 or something, about 55 degrees Fahrenheit. So we're going to use cold water for this demo, and we're going to record that temperature in our lab under the cold water beaker temperature. So we're going to go ahead and use 7 degrees C, and so go ahead and write that in next to the cold water beaker temperature for part 3. And what we're going to do is we're going to time how long it takes for the food coloring to disperse through this liquid. Now you can see I have a stopwatch here. I'm going to use that here to demonstrate how fast this food coloring moves through. So hopefully we'll be able to see exactly, oh boy, I'm fumbly here. We'll be able to see how this all pans out. So we're going to look for the food coloring to disperse pretty evenly through the liquid. So here we go. Oh boy. Source of error there, my stopwatch. was pretty touchy. Now that's pretty cool, right? To watch the food coloring disperse through the water. Note that it's sunk way down, and now it's kind of splashing back up and moving around, but it's really in drizzles. It's not really kind of dispersing out amongst the rest of the water. It's kind of more in fumes here. It's taking it a while to reach around. And as we watch, the clock keeps ticking. And we're kind of looking for dispersion throughout the entire liquid. Judging a little bit, it's a little bit hard to judge when that is, but we'll keep our clock running here. And the food coloring is starting to make its way down and through the liquid. Still just ribbons of food coloring, not really dispersing amongst the liquid. When you have a cold atmosphere, the molecules aren't moving very fast, and so things don't disperse very well through that because the molecules aren't moving very fast. Cold temperatures equals slow moving molecules. That would be what you would see in a Jovian planet, for example, with a cold atmosphere. We're going to go ahead and stop it right here, even though it's still struggling to disperse through. We're getting close to dispersion here. Still pockets of clear water, but we'll go ahead and stop the stopwatch, I guess, right about now. And we got about 1 minute and 56 seconds. So under dispersion time, next to cold water beaker, you're going to want to write 1 minute and 56 seconds. All right, we're going to do the same thing, except we're going to make this water hot. All right, so here give me a second here to replace the cold water with hot water. All right, here we are with our hot water beaker, 200 milliliters of hot water, and I've got the thermometer in there. I'm going to pull it out really quick and measure the temperature quickly because the temperature goes down very rapidly. I can see right here that the temperature is about 119 degrees Fahrenheit, or about 47 degrees Celsius. So you can take my word for it. You can see here we are, boom, there. Look at how fast it's going down. It was at 47 degrees C. Now it's all the way down to 42 degrees C and so forth. So in the temperature for hot water, write 47 degrees C. The cold water temperature was 7 degrees C, but we're going to write 47 degrees C for the hot water beaker. And we're going to go ahead and bring in our red food coloring here, and we're going to bring in our trusty stopwatch. Okay, and let's go ahead and drop in some hot water. Drop some food coloring in hot water and see how fast it disperses. So here we go. All right, we see similar ribbons of color as we did before. Really cool looking, right? But look at how much faster that's dispersing. If you go back and look at the cold water dispersion, it was much slower. But this, because the molecules in the water are moving faster, they're bumping against one another faster, it's causing the food coloring to disperse quicker. In a warmer atmosphere of a planet, the molecules in that atmosphere are moving faster, and you're going to have, therefore, a warmer temperature. So now we're pretty close to dispersed here already. If you compare where we're at now with where we were at with the cold water, we're pretty close to dispersed. I'm going to go ahead and hit that at 51 seconds. So for warm water dispersion time, we can go ahead and write 51 seconds. Whereas the cold water dispersion time was 1:56. This is more like just under a minute. All right, so we'll go ahead on to part 4 after this. Okay, the lab part 4 deals with the Coriolis effect. And you see this section here, it gives a description of how atmospheric circulation takes place, how the air rises in the warm areas and sinks in the cold areas. And when the planet spins, it deflects the winds and causes them to curve and swirl. So the part here is to actually spin a chair and have the piece of paper in the chair and have a marker going out as you spin. Now, it's very difficult to do, but I'll show you the general idea. If I was to take my pencil or my pen here and go put it right here in the middle and go draw slowly outward as I spun the chair around, like so, okay? As I spun the chair around, I would draw a line outward and see what would happen. I'm gonna spin the chair slow and then fast. I would start in the in and move outward, going slow, and I would start in the inside and move outward going quickly, and then I would do that starting on the outside of the paper, moving inward, slow spin, and starting on the outside of the paper, moving inward, a quick spin. And I'm going to show you what that looks like, the results. It's very difficult to do, so I did it in advance, and I'm going to give you just a look at what it looks like. Okay, I went ahead and did the spins for you and drew on the pieces of paper. From the inside going outward slow, you get this little curve here. From the outside in going slow, you get another little small curve. If you spin the chair fast and put the pen in the center and go outward, what you actually find is that you draw a swirl. So the faster you have a spin, the more swirl you have. And then, again, outward in, swirling very fast. And in fact, if you spin fast enough, you're going to create bands. So you can copy each of these into the spaces here in the table. And it says to describe the differences in swirl tightness. Obviously, the slower speed, it's not a tight swirl. And the faster speed is a tight swirl. And then it shows you 3 planets, Venus, Earth, and Jupiter, and the cloud patterns of each. And you see this gentle curve here on Venus. If it's got a gentle curve, what kind of speed is it swirling? Or excuse me, yeah, what kind of speed is it rotating? Not very fast, right? In Earth, you see a curve with a swirl like this, these big swooping curves with swirls in them. So Earth's moving a little faster. And Jupiter, you can't really see it maybe from the camera angle, but Jupiter is swirling so fast that there are little swirls, and the swirls make up little bands. And of course, this big swirl right here, the great red spot of Jupiter, is another example of one of those swirls. Jupiter is rotating really fast. Jupiter rotates about once every 10 hours, and that's really fast for a big boy. So Jupiter, again, is going to give us those tight swirls, so tight that they form into bands. So I ask you to categorize these from slow spin to fastest spin based on what you, fastest spin with the number 1 to the slowest spin with the number 3 based on the curvature of the clouds and the atmospheric patterns. And obviously Jupiter spins the fastest, then Earth is number 2, and the slowest spinning number 3 would be Venus. So that's this part of the Coriolis effect.